Okay, hi everyone. Welcome to today's condensed matter seminar. This is our last condensed seminar this semester, but definitely not the least. My name is Elucidating. I will be the host today. So it's my great pleasure to introduce today's speaker, Professor Matthiew Gilbert. Professor Gilbert is an associate professor in the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign, UIUC in short. He is affiliated with the Micro and Nanotechnology Laboratory, the Department of Physics, and the Institute for Condensed Matter Theory at UIUC. His research broadly focuses on theoretical elucidating new phenomena in emergent materials with the goal of developing new types of next generation information processing systems. The majority of his current work revolves around understanding the property of topological materials, including topological insulators, semimetals, and superconductors, with the goal of understanding their potential role in high-frequency electronic, magnetic, and quantum computing applications. He is part of the Department of Defense Advisory Group on Topological Electronics, and he's also the founder of a startup company that works to design topological metamaterials for high-frequency device applications. So today, Matthiew is going to tell us about some interesting phenomena of materials where magnetism meets topology. So without further ado, Matthiew, please take it away.
Great. Thanks, Shule. Thanks very much for the very kind invitation to give the seminar today. Let me get started. Okay. So actually, I think I have to share the screen and then I can. All right, can you see this screen okay?
I see.
All right.
It's fine.
Yeah, I can see it.
Okay, perfect. So as I mentioned, thank you very much for the kind invitation to come and address you guys this morning. So just as a bit of background, so if you may recognize the lovely lady in the upper right hand corner. It turns out so that I was really interested in anthropology when I was graduating high school, and I wanted to go to Case Western because Donald Johnson was a faculty member, and I thought this would be the perfect place to go. Of course, it didn't work out, but it seems like things worked out okay for anyways. I didn't go into anthropology, obviously, but I still appreciate this is, I think, is this Australopithecus afarensis. This is Lucy. And this is the big discovery that he found in 1974 in Ethiopia. So enough about Lucy, though. Let's talk about more about physics. So as Shule mentioned, I'd like to tell you some of the work that we've been doing about looking at topological systems that have magnetism, either in this case, either imprinted through proximity coupling to a ferromagnetic system, or in terms of inherent magnetism, but as driven by doping. So these are some of the representative publications, and this is the outline of the talk that I'm going to go through today. I think the easiest way to understand the interplay between magnetism and topology is to study a system that is sort of well known both theoretically and experimentally, and this is the Churn Insulator. So first we'll go through a brief introduction of Churn Insulators, and on this I hope that since we're maybe a more intimate group today, it would be nice to know sort of your general level and comfort with topology, because I think since this is the last seminar this semester, I think I don't want to leave you with a confusing talk. So I'd rather sort of take some time and spend thinking about some of these basic aspects of topology, rather than just sort of charging through yet another talk that at the end may not have any sort of impact on the way that you think about things, and that if possible, I'd like to avoid that. So please let me know, because we can certainly go through some other aspects of topology before we just go into the main part. That was my contribution. And then we'll talk about some of the effects after the Churn Insulator. We'll talk about what happens when we start adding in magnetic systems or magnetism to the topological system. And one of the important consequences is it introduces non-Hermitian behavior. And so we'll discuss a little bit about how these systems change when we start to consider non-Hermitian effects. But what I hope to show is that by the time we finish the first couple of sections, then I will have presented a paradox. And in the third section, we hope to, I will try to clarify this paradox and explain to you how we can reconcile the theoretical understanding that we have with the experimental understanding. And then finally, if we have time, we'll go beyond reconciliation to talk about some of the more recent topics and more recent developments. So as always, please stop me and ask questions if there are any. So Churn Insulators. One of the overall goals is there exists a large class of systems with it, which I think from a physical perspective, I think is something you can qualify as well-known. And by that, I mean, it's a system in which the invariant and many of the important properties are well understood. And so in that sense, physicists generally don't tend to do too many more experiments on them in their sort of native form, but it still doesn't mean that they're done, and they may have some future role to play, as Shile alerted to when he was going through my brief introduction. So one of the things that I've been trying to do is find a way of taking these sort of known topological materials and trying to bridge the gap between physics and applied physics to try and get more people interested in looking at experiments or theoretical constructions using these materials that people consider to be well known. And so people have done some work designing devices using basic topological materials like bismuth selenide, bismuth telluride, but it's really just starting. And one of the properties that seems most interesting are the magnetic properties, and we've been doing some work on the magnetic properties. This was a paper that came out a few years ago that discusses how we can use magnetic interactions with topological insulators to make very, very efficient energy storage or inductive devices. So this has been something that we've been thinking about for a little while, and the way this works is really by exploiting the Axion Electrodynamics that are present within the topological insulator. So just in a very brief sense, these Axion Electrodynamics, can you see the cursor as I move it around? All right. So the Axion Electrodynamics here, if I were to have a topological insulator, which is three-dimensional, all the surface states are gapless. And if I were to put a ferromagnet and encase this topological insulator with magnetism pointing perpendicular to the plane at every single point, then I gap the surface. And if I apply an electric field, then basic considerations would say that I don't expect to see a longitudinal conductivity because I've gapped the system everywhere. However, because of the fact that there is an E dot B term, so this Axion electrodynamics within the topological insulator, it means that when I push current through, it doesn't go longitudinally, but becomes a Hall current, and the Hall current then rotates around the system, as I'm showing here with these arrows, and it rotates around the system, producing a magnetic field which is in the same direction as the electric field. So then I have an E, and I have a B term that point in the same direction. This is where you get this E dot B, which is the bulk invariant for the three-dimensional version of a topological insulator. And there have been many other studies hence that have talked about how magnetic interactions give rise to large spin Hall angles and other sort of associated properties. So to start, let's talk about the Churn Insulator. So this is work that Duncan Haldane had done in 1988. It's a very famous work where he took graphene before graphene was really a thing, so two-dimensional form of carbon, and he included a magnetic flux, but the magnetic flux, there was no net flux through any one of these plaquettes. It was only a periodic flux. And so what he did is he took the original graphene Hamiltonian shown here, which is the normal Dirac equation, and there is a mass term at the very end that comes from the presence of the magnetism. And so, as a typical question in any sort of qualifying exam is, what protects the symmetries of what symmetries of graphene are present to protect the band crossing. And so in graphene, of course, the symmetries that are present are time reversal invariance and inversion symmetry. And if I have both of those, if I break either one of those, then I can still, I can add this m sigma z term and I can gap out the system, but it's really only when I have both of them preserved, the combination of the two, I can't add this m sigma z term, and so the system remains gapless. But if I apply this perpendicular magnetic field or this non-zero periodic magnetic field to the system, then I add this mass term and I break the time reversal symmetry, but I still have preserved inversion symmetry. And so I have the two Dirac cones at the K and K prime points, but in this system, because of the fact that I have broken time reversal symmetry, but I have preserved inversion symmetry, that means that this mass has to essentially change sign as it goes from one Dirac cone to the other Dirac cone. And so this change in sign leads to a mass domain wall that's in momentum space that gives rise to the quantized edge conduction that looks like I have a Hall effect without the presence of a quantizing magnetic field in order to quench the kinetic energy of the system. So this is a difficult thing to do normally in 2 dimensions. So we have to look to other materials to be able to form a Churn insulator. So adding magnetism to 3-dimensional systems is something that's been done for quite some time. Even in certain processes, you get the magnetism even when you don't want it. And so in normal 3-dimensional topological insulators that are protected by time reversal invariance, if we were to add magnetic impurities into the system, then you would not expect to see any gap open because I haven't broken the time reversal symmetry of the system. And so what we see here is you see these non-magnetic impurities that are added into the system. And if you look at the ARPES, you can still see a well-formed Dirac cone and a Dirac point. The Dirac point for bismuth selenide is closer to the valence band anyway. So it's not particle hole symmetric in the same sort of way that we think about when we construct simple 3-dimensional models that have an appropriate Clifford algebra representation of them. So even though, this is sort of, this is experimentally done, you still need to have some very loving eyes to sort of look at these things and see, yes, clear Dirac point. It's something that takes a little bit of faith. But if I were to add magnetic impurities, then something interesting happens. So again, these are things where only the loving eye of an experimentalist would really say, yes, okay, clearly there is a gap here. It looks like there's a great deal of spectral broadening that occurs as I'm inducing additional quasi-particle lifetimes into the system by adding in these magnetic impurities. So I go from a system that is gapless with a normal bismuth selenide to now a system that has a gap in it. And the gap forms because of the fact that I have these magnetic impurities, which overall have a net magnetization that points out of the plane and breaks the time reversal symmetry of the surface. Okay. Other ways that we can get magnetism into 3-dimensional systems would be by just simply doing magnetic doping. And so for magnetic doping, what we can think about is just sort of impurity doping, but then instead of using a field or requiring the impurity atoms to, on aggregate, have some field that points in one particular direction or another, what we can do is we can dope it and then use the RKKY interaction in order to be able to orient the dopants out of plane and give us the proper orientation, so we can add iron or chromium, vanadium. The chromium and vanadium are the two that you'll most often see in the literature. So each of the individual spins then would not align, but if I have the proper concentration, then what happens is I can get the spins to align using the RKKY, as I've mentioned before, the interaction there. And but I need a critical dopant density, and that critical dopant density does result in the ferromagnetic ground state, but it requires the spacing between these atoms, the magnetic dopants, to be quite small. And that's very difficult to achieve experimentally. So this is probably not the ideal way of doing it, where you dope it so heavily that you can take advantage of RKKY interactions. And in fact, what's been done is that they have used these chromium doped materials, and they have imprinted them into a ferromagnetic, into a topological insulator, and then used a magnetic field to orient the dopants so that they have a net magnetic moment out of plane. And then, of course, once they orient the spins of the chromium dopants, they remove the magnetic field. So chromium doped bismuth selenide then becomes a candidate where you can see Churn insulator behavior in a three-dimensional topological insulator. So a good question to sort of just to sort of check and make sure that we have a good idea of what we should be expecting. It seems like in this case there would be something a little bit odd about this, because if I think about a three-dimensional system with a series of gapless points on all of the surfaces, then the question becomes, where would I expect the edge state to come from? And in this case, for the three-dimensional topological insulator, it comes from the fact that I have a bottom surface that has one Churn number, so Churn number -1/2, a top surface that has a different Churn number +1/2. And so as I go between those two Churn numbers, then I necessarily have to have a mass that is going to change side. And so I apply the magnetic field, I gap each one of those surfaces differently. One case, I'm going to have one of the cones go down. The other case, I'm going to have the cone go up. And so as I achieve that mass gap, which goes from minus to plus on both these surfaces, as I go around the topological insulator, I necessarily have to have that mass gap go to 0. And when it goes to 0 is where I see the edge state show up, or at least I expect to see the edge state show up. And so in the system, when they make their transport measurements, you can see that it looks like they have signatures of a state that is consistent with a quantum anomalous Hall effect. And that's one of the nice things about topology, is you don't have to really make a lot of guesses. There's either a hole in the mug, or there is no hole in the mug. There's no half a hole in the mug. It's either 1 or it's a 0. It's quantized or not. And so the Hall conductivity looks like it's very close to quantization, but there is a problem with the longitudinal part of the conductivity. And if we have a properly formed Hall state, then we would expect to see that longitudinal conductivity drop identically to 0 while we see quantization in the Hall conductance. And you can see very clearly that doesn't happen here. And so there were a lot of theories that had sort of discussed, potential reasons why you don't see identical quantization. I had my own pet theory where I thought that it was simply because of the fact that you have these magnetic impurities. And so if I were to scan along the edge of the system, then on aggregate, I would expect to see some rotations, and there may even be some rotations as I flow a current across the system due to some sort of a torque effect. So I thought that the gap was sort of smaller, larger, open, closed as you moved along the edge of the system, leading to non-quantized conductance. But it turns out it's actually a much simpler argument than that. It's just that there's some self-heating that occurs when you try to flow too much current flow through the system. And this is shown quite nicely in some experiments from David Goldhaber-Gordon's group at Stanford University, who did these very nice and careful measurements showing that as you drop the amount of current bias in the system, that the longitudinal conductivity begins its precipitous descent towards zero, as we would expect.
Matthew, I have a quick question.
Sure.
The previous slide, the magnetic atom, you mentioned that they are coupled by the RKKY. And
no, not in this case.
Okay.
But no, this is.
I have that yeah. So the RKKY, I mean, maybe not this case, maybe for the previous case, the RKKY depend on the separation between the magnetic impurities.
True.
It could be ferromagnetically coupled. It could be antiferromagnetic coupled. So I'm just wondering if this will make a difference if the magnetic atoms are antiferromagnetic coupled.
Antiferromagnetically coupled would be a very interesting situation. It would in a sense, there are a certain number of games that you could consider playing if you did have antiferromagnetism that is native. And so this is some work that we've been doing a lot more recently that I had hoped to talk about, but there was an experimental issue with one of the submissions. If you have a commensurate antiferromagnet, so something where I can identify a translation vector between the different successive magnetic moments, then what I can have is I can have a combined time reversal symmetry plus magnetic translation, which would lead to the ability to stabilize a band crossing in a three-dimensional system or two-dimensional system. So there would be commensurate antiferromagnetism, but this is not necessarily very interesting because you would still only have the traditional Z2 type of invariant, and so you would expect to see some bulk charge polarization or something that is the invariant. So a more interesting case would be if you imprinted the antiferromagnetism and you were able to imprint it into a system that had where there was a way of getting maybe very strong interactions between the magnetic atoms and the itinerant electrons, where you may be able to drive it into a semi-metallic kind of phase. And so that would also be interesting. But that I think is a lot more of a difficult challenge. So I would say that, yes, it is interesting because if you could imprint the antiferromagnetism, then there are some things you could do. Vial semimetals with antiferromagnetism is a very interesting system. But in this case, I think the ground state for the magnetic impurities that they were considering in the paper that I think this was a Shouchen Zhang paper from a number of years back. I think the magnetic impurities they were considering there, the ground state was ferromagnetic rather than antiferromagnetic.
All right, thanks.
But in this case, it's more dilutely doped. So you don't have the potential of having the interactions where you can drive them into the ferromagnetic phase. So before they make this measurement, then they have to apply a magnetic field to orient all of the spins out of plane, and then it breaks the time reversal symmetry of the surface.
Okay, thanks.
Are there any other questions before we sort of move on, or is everything okay? Okay. So one of the things that I think is safe to say is that if I dope a system with magnetic impurities, then it's certainly going to set a boundary on how high a phase I can expect to see this magnetism retain its ferromagnetic state. And one of the big issues that the Department of Defense had been working with was they very much would like to see a room temperature quantum anomalous Hall phase because you can do all sorts of interesting things with that. But one of the difficulties is that in this case with the doped system, there's not really a clear path for that. So one of the big issues then becomes, well, we have a large number of ferromagnets, and these ferromagnets have a lot of interest in sort of basic physics, but there's also implementations of the quantum anomalous Hall effect might be possible because these ferromagnets retain their magnetic behavior well above room temperature. And so if the system retains its ferromagnetic behavior well above room temperature, and I can create a topological insulator that is bulk insulating, because normally the selenium vacancies add electron doping to the system, and it makes it sort of to a metal where the bulk is clearly not insulating. If I can properly design one of these systems, I can certainly see the topological phase be present at room temperature. So if I were to break the time reversal symmetry by using this ferromagnet that's proximate to this, then it's possible for me to change the energy scales at which I see this type of interesting physics. So then this precipitated a large amount of work that's been done to try to couple bulk ferromagnets and use the exchange interaction between the ferromagnet and the interface to spontaneously break the time reversal symmetry. So the non-local Coulomb exchange interaction breaks the time reversal symmetry on the system, on the surface spontaneously, and you would see the gap form, and we should be able to then see the quantum anomalous Hall effect. And a lot of this, I think, was based on sort of the enthusiasm that people could get from the proximate coupling between topological insulators and superconductors, where the long coherence length of the superconductor would allow the tunneling of Cooper pairs deep into the topological insulator, where you could reasonably expect to see superconductivity appear on both surfaces of a topological insulator if it was relatively thin. So here, I think the hope was also along the same lines, where since topological insulators have very strong spin orbit interactions, they're sort of close to sort of, you could say, maybe perhaps a magnetic instability, that the imprinting of magnetism would have as positive a fate as that it did for the superconducting systems that are also proximately coupled. So a lot of work has been done on this, and I'm only going to highlight a few things because I don't have time to go through all of it, but there's a large body of literature on coupling things. And this is one of these circumstances where happily the experiments are able to lead the theoretical efforts in some sense. So there's no shortage of interesting experiments to be able to think about and compare the work to. So one of the first was this interesting paper on europium sulfide that has been magnetically, this MBE grown on the surface of a topological insulator. And there have been some, this is a very, I would say, controversial result because it has a very odd implication. So the Curie temperature for bismuth for the europium sulfide is 17 Kelvin. But if you look, and I think this is neutron scattering that was done at argon. And one of the things that's very curious about this is that even though the Curie temperature is very tiny, they can still see signatures of magnetism imprinted into the topological insulator at room temperature, which doesn't really make a whole lot of sense. And so there's been some work to try and understand exactly why this is, but I think that the case is still a bit open. I have my own pet theory that I'll tell you about. I guess I'd tell you now that my theory is that that it is really the fact that, you know, the europium, and so it depends very heavily on the growth, but the europium moments are very close to the interface. So I think that there is an argument to be made that has to be, you know, quantified, but there's an argument to be made that says that the europium moments close to the surface will drive a magnetic transition, or can drive a magnetic transition, but that the bulk of the ferromagnet doesn't necessarily play the role that we had hoped that it would. So this is an ongoing debate, and I think that there are some, there should be some interesting work that comes out on it fairly soon. There have also been some questions about if we put an even higher temperature ferromagnetic system on the surface, then we maybe give ourselves better chance of seeing these interesting quantum anomalous Hall states, but still no. And so it really comes down to the fact that, so if this is thulium, so TIG, thulium iron oxide, grown on bismuth selenide. This is again from MIT. Both these experiments are from MIT, really done by Jagdish Mudera. But when you look at the system, you'll oftentimes see the anomalous Hall effect be plotted. But that simply means that you've broken the time reversal symmetry of the system, and you have broken SU2 and broken time reversal. And so when you have that, then you can see an anomalous Hall effect, as they do here, well above room temperature. But they're not showing you the quantum anomalous Hall effect. And so that means that they have not been able to successfully allow the exchange interaction to take place on both surfaces, both the top and the bottom surface. So there's obviously some screening effects and other things that take place there that make it very difficult to get that to work. So now what I'd like to do is move on to the argument for non-Hermitian topology. So right now, up to this point, we've been considering a completely idealized view of how to calculate, how to think about topology. But this is not really the case, and so we have to consider something a little bit more concrete for the system that we're actually interested in. And by that, I mean, we don't have just a system sitting in isolation. We have a system that has a reservoir, and this reservoir has the possibility of exchanging quasi-particles between itself and the system. And so anytime I have a quasi-particle exchange between a reservoir, then I have an open system, and I'm imparting a quasi-particle lifetime into a state that normally in isolation would have a quasi-particle lifetime, which is infinite. So that means that there can also be systems of loss and gain that we haven't really taken into account in these systems so far. Oftentimes, when we think about these, we assume that the overlap between the phonon interaction and the electrons or the electronic wave functions is small enough where we don't really have to consider it. But that doesn't necessarily have to be the case. And so we have to reformulate the way we think about topology to include the openness and the possibility of loss and gain. And this is really where we get into this adjustment of topology that had to occur a few years ago. Before we get into the adjustments and their implications, we want to understand the implications of having quasi-particle lifetimes. Normally, when we think about topology, we think about Green's functions or more complicated field theoretical constructions of what exactly we're doing. So we can start by defining a simple Green's function, which is the retarded Green's function. Here is a Matsubar Green's function, so finite temperatures for some omega. And we would like to think about what happens when we add the lifetimes in, which means that we have an interaction. We could be electron-phonon, electron-electron, impurity interaction, something that we've added into the system that take the infinite states and turn them into finite states. And this normally comes from when we take the Hamiltonian, we have the bare Hamiltonian from which we would normally get the undressed Green's function. And we add to that the self-energy term, which incorporates all of these different interactions at various different levels, born, second born, whatever you want to do. And so the self-energy then has two parts to it. So you could think about the the quasi-particle coming from an interaction. When I add this interaction in, then I take my energy and I break it up into two different pieces, a real and imaginary component, each one of which comes from a different part of the self-energy term. So the self-energy term also has a real shift in the quasi-particle dispersion relationship, but it also has the quasi-particle lifetime that it imparts, which is the imaginary part of the self-energy term. So this is what we would like to start thinking about. And when we start by thinking about these interesting systems, then we have to extend what we know about topology. And so we need a few different definitions in order to really be able to classify what's going to happen and contextualize it with what we already know. So we can start by defining what a separable band is. A separable band is something where I simply don't have any of the same eigenvalues at the same points in space. So I can have them, but they don't occur at the same, I can have them at different points in the Brillouin zone, but they don't occur at the same point. So I have no band crossing points. Or I could deal with isolated bands. Isolated bands is more what we think of when we have like an insulator or a semiconductor or something along these lines, where I neither have the same energy eigenvalues in the Brillouin zone, but I also don't have them at any point in the Brillouin zone. So not at the same point or any point. And so these are isolated bands. And there's been some really nice work that has thought about the basics of this. And if I have a non-Hermitian Hamiltonian with a self-energy in it, that means that I don't have the same picture where I can have the left and right eigenstates so are going to be the same anymore. There's no orthogonality condition that's necessarily going to occur. And so we have two sets of eigenstates, sort of a left eigenstate and a right eigenstate, and we could combine this into 4 different types of Churn numbers. But one of the things that seems like it's a little bit non-intuitive, but it's a solid mathematical result, is that each one of these are identical. So even though we have this non-Hermitian Hamiltonian, which we've now introduced into our system to talk about topology, the Churn numbers that we're able to define seem to be the same. And so if this had no consequences whatsoever, then the talk would have ended here and we'd have gone on about our day. But there are some other consequences that we have to consider beyond simply the definition of the Churn number. So in the Hermitian sense, the Hall conductivity is intimately related to the Churn number. And in the quantum Hall system, or in the Churn Insulator, certainly the Hall conductivity or the edge state is the invariant in the system. And so what we'd like to ask is, if even though the Churn number doesn't seem like it necessarily changes, is the link between those two things still legitimate? And so we started by thinking about this using the Kubo-Strata formula, but we can't necessarily apply the Kubo-Strata formula any longer because of the fact that we have this quasi-particle broadening, which makes it very difficult for us to identify occupied and unoccupied states in the system. Normally, when we have the Kubo-Strata formula, we can simply make a transformation and map this onto the more familiar form of the Hall conductivity in terms of the Berry curvature of the system. So we can't do this, so we have to go back and think of it in a bit of a more complicated way, which also serves to show that we understand enough about the system where we can derive these sort of invariants in several different manners. But particularly, we have to take a step back towards the more basic field theory of the system. And so we can still define an action, and the action still has the same sort of U1 invariance that we have before. And so when we do this, we can write down our Chern-Simons action here, and by applying the Ishikawa-Matsuyama formulation, we can take this action and we can convert it into the this invariant that I'm showing you here, this K invariant. This is the same thing as the invariant that I'm showing you here, believe it or not. These two things are identical. So there are some issues with using Ishikawa-Matsuyama formulation in that in order to get from the action to the invariant, what I necessarily had to do was apply the Ward-Takahashi identity, which is another way of saying this is a quantum form of Nether's theorem. And this is a conservation law, which means that in this case, I would expect to be in a current conserving formalism, where in a non-Hermitian sense, I am definitely expressly saying that I may not be conserving current. So how do I reconcile these two things? And the way that I can reconcile this is by thinking about the definitions of these things mathematically in terms of local and global properties. Obviously, the Ward-Takahashi identity for current conservation is not going to necessarily hold in a local sense, but it will hold in a global sense. And this is a global sense is where the sense that I'm using in order to be able to define this U1 invariant action. So we're seemingly on good foundation to be able to apply this formula mathematically. And so really what we want to do is we want to calculate this two-leg fermion loop for the Feynman diagram is the one that I'm showing here, this polarization tensor from the two fermion loop. And this is the integral that results as the antisymmetric part of this polarization temperature gives me the conductivity that I'm most interested in from the current correlation functions. So this is what I would like to start with as the foundation, is this action. And what I'd like to do is take and construct the Green's function based on this insight. And I still should be able to use this, this mapping. But the problem is that there's a failure. And this failure is a little bit subtle. And so let me illustrate to you here what this failure is mathematically. And then I'll tell you in a second how we can think about this in a more physically concrete manner. So what I'm saying in this particular graphic here is that if I were to take the continuous case, or which is the R3 case, so it's R cross S2, so the two sphere, but in reality, I'm just lazy and I should probably have just read S3 or R3. But either the continuous case or the discrete case. So in the continuous case, I can take my N loop and I can assume that when I map this into my target space, then the closure that I require in order to define my target space manifold is taken in the continuous case by the boundary, where I map every point onto the boundary, and that gives me the closure that gives me the pinch for the three sphere. In the two sphere, or in the continuous case, then the pinching that I do from this homeomorphic mapping comes in the form of a torus, but everything else is more or less the same. And this torus, in terms, so in the three sphere, it's maybe more simple to see that when you do this pinching, you're going to have the pinching will close at infinity, and this closure at infinity as k goes to infinity. This pinching gives me three loops, and the three loops allow me to classify a homotopy group based on this three loop structure. And the homotopy group for the three loop structure for both of these systems is in the general linear class, where n is the number of bands and c is the complex number range. And I can map this into, I take the third homotopy group of the general linear class, and I get a z invariant, which of course tells me that my system should be quantized and the invariant should be quantized. But there's an issue. And if we take this by breaking this Hamiltonian up into the Hermitian and the anti-Hermitian components, which I've done because I've added the self-energy term in, then in order to preserve causality, it requires the broadening to contain a positive diagonal component. So this is the self-energy term that I'm required to include in the system. And when I map this onto my Green's function, then the problem becomes that the self-energy is entered into the system as in the form of this signum function, and the signum function has a discontinuity that occurs at zero frequency, zero imaginary frequency. And so if I were to define a topological system, as I do for this mapping that I discussed on the previous slide, then I expect to see continuous Green's function continuity, especially as I pass through zero imaginary frequency. But in the topological case, what that means, or the non-topological case, that means that when I include this self-energy term, I break that interaction, and the discontinuity that forms because of the self-energy inclusion means that I can no longer continuously homeomorphically map from the Green's function in the topological case to the non-Hermitian case, and so topology breaks down. And so from this, you kind of think, well, where would I see such an interaction? So it's really a non-Fermi liquid-like interaction that really is required in the self-energy term to break the topology of the system, which is why in many cases you still expect to see the sort of interactions. But there are ways of adding these in, and magnetism and magnetic impurities is certainly one of them. So we see this homeomorphic mapping breakdown. But I'd like to give you a more physical sense of what happens by considering a very simple system, a two-level system. And in this two-level system, I'm just going to write down a basic simple Hermitian Hamiltonian. And without making any sort of arguments beyond this. I can simply calculate the invariant by looking at the winding around the 2 sphere. So this is the winding of the spin specifically around the 2 sphere. And this is swept out by it's the angle subtended by this D vector here that I'm defining above. And so for the generic, I just added a generic non-Hermitian term. Okay, I've made no preconditions as to the form of the non-Hermitian term that I'm adding. In fact, I'm not even making any sort of preconditions as to the form being discontinuous or continuous. So when I add in this non-Hermitian interaction of just a simple generic form, and I do a very simple mapping to just sort of take this and put it into a slightly different form to make it a little bit more visualizable, I see that my Hall conductivity, so my invariant that I calculate by looking at the winding, contains a topological part, which is the part that we expect to be there. But in any case, I still have some component of non-topological character that enters into the formula and gives me something where now I have a loss in the quantization of this conductivity. So we can illustrate this again by taking a more complex example. And in this complex example, just using the Dirac equation, a massive Dirac equation, we add in the self-energy term. We can construct the Hall conductivity and unfortunately, also the longitudinal conductivity. And when we plot these out, you can see the transition as we go from perfect quantization here, where I'm looking here at one surface, so I have the half here. I look at one surface, I have the half here, and so as I add in any component of broadening into the system, then I lose this connection between the topology of the system and the Churn numbers. The Churn number will remain quantized and invariant as long as I have this system, but the invariant that I expect to see is no longer there. So this means that there's a bit of an odd disconnect. And so what I want to do now is, I think, hopefully, what I've done is I've painted a picture, one in which case I have an experimental system that shows very clearly that I have quantization. And I've made another case that I hope was compelling, that says that if I have broadening into the system that is induced obviously from impurities and certainly from magnetic impurities, then there has to be something that says that these two things have to coincide at some point. One says that I should have, the experiment says I should have a quantized conductance. The theoretical component says that there should be not a quantized conductance. So how do I reconcile these two things? Obviously, from a theoretical perspective, then that's the experimentalist's job to explain. But they don't often see it that way. Of course, like in reality, the experiment is the ultimate arbiter of whether or not your theory is correct, because all theory is wrong. It's just a matter of degree. However, I would argue that all experiment is correct if it's true, if they truly understand what it is that they're measuring. That is not always the case. But I think that these two things are something, certainly in terms of topology, something that must be reconciled. And so what I'm going to try to do here is show you how these two things coincide. So we need to do something a little bit less fancy mathematics and more concrete. And to do this, we simply assemble a tight binding Hamiltonian, and we keep the momentum directions, two in-plane momentum directions in momentum space, and one real plane direction out of space. And we can write down the Hamiltonian for a ferromagnet very easily, just a metal or an insulator with a magnetization. And we can couple that to a topological surface state and with some coupling. And what we should be able to see is we can represent this ferromagnet as a self-energy term. And this is done for convenience in some sense, but naturally when we collapse everything into a self-energy term to represent the reservoir, what we have inherently done is lost some information in exchange for this simplicity. And so in this case, you may ask, well, where is the simplicity that's what has been lost here? And it's a little bit subtle. So the information that we lose is actually the information contained in the entanglement of the system. So when we add this self-energy term, no longer are we really able to discuss things in terms of entanglement. And if you were to classify a topological system, then the easiest way to do so is by thinking about the entanglement. So when we put the self-energy term, the entanglement is no longer something that it's no longer trackable. I would say all that information is lost in the simplicity of the self-energy. So what we hope to do then is to calculate the spectral function using Green's functions and say something about what we see in terms of being able to do a very simple calculation to go between the experimental and the theoretical pictures. So when we look at the surface state spectrum, it's quite straightforward. If I have an insulator, then I see that if the mass gap that opens is approximately twice that of the hopping, so in this case, I mean, the magnetization has to be twice that of the hopping, and I can start to see a gap open, but it's very small. So this is the local density of states here for the insulating system, and this is the spin expectation value. And so for the ferromagnetic insulator, the ferromagnet is pointing out of plane perpendicular. And so it's interesting to see that the magnetic ground state that shows up is an antiferromagnetically ordered one, where the magnetization of the topological insulator points opposite direction of the ferromagnet. But it's a very small gap that opens. And in fact, it's difficult to see in most of these plots. You have to zoom in quite a great deal. But if you take the magnetization, make it less than the hopping, then you're turning this back into a metal, and you can start to see the states broaden out here. But if you look at the local density of states, it looks like I've simply broadened everything together. And so if you were to calculate the same values for the spin expectation are observed, but when you look at the actual energy spectrum, then in the real spectrum, you see the gap. But what you've done by including this spectral broadening is you've taken the eigenstates and you've shifted them into the complex plane. And so even though there's a gap, there's now you've shifted these eigenvalues, and there's some imaginary term that enters into the Hamiltonian. So how do we explain this in terms of being able to observe the quantum anomalous Hall effect? So we did this by trying to go back to the Kubo-Strata formula for our system, where we have a ferromagnetic self-energy term connected to the surface of a topological insulator. So we have three basic components of the Kubo-Strata formula. The first two deal with the Fermi surface terms. This one in a Dirac system goes away by symmetry, but this one is the Fermi surface term, which includes the Berry curvature and also some of the processes that are required for anomalous Hall conductivity, and the velocity operators are all included in the Fermi surface terms. But in a topological system, the most important contribution comes from the Fermi C term. And this is really where you start to see the effects of topology being a truly non-local phenomenon, where you have to integrate over all of the occupied states in the system in order to be able to define a Fermi C term. And so this is the term that is responsible for the quantum anomalous Hall effect, and it is only quantized when we have a perfectly gapped system. So when we consider the Fermi C term, we want to think about this, and for the very simple case of a self-energy term where there is no spin-orbit coupling in the Fermi's self-energy term, then I can write it in a diagonal form and come to a closed form solution for the Fermi C term of the conductivity. And we can see that when the broadening is non-zero, the Fermi C term is no longer exactly quantized. But what we see is that if we check the limit as the broadening goes to zero, we recover the correct form. So this is a good sanity check to make sure that we've done our integration correctly. The Fermi surface term then is also going to play an important role. And as I said, there are three terms, one of which though is going to cancel by the fact that it's odd in momentum. So we have the broadening term that's added into the Hall conductivity that we calculate using the cubostrata approach when we add in the self-energy term, and then we can get a closed form solution that has the fact that when we take the broadening to zero, we recover the correct form where the Fermi surface contribution goes to zero, and all we have is a Fermi C term. So how do we think about the loss in quantization then? If I were to plot this out for different types of broadening, then you can see in this case here, when I have no broadening whatsoever, then the conductance is perfectly quantized until I get to the edge of the energy gap that I have opened in the surface state spectrum of the topological insulator. And when I reach the sort of bulk bands, if you will, then the conductance starts to become non-quantized, because not only do I have a Fermi C, but I have the Fermi surface term that starts to contribute. So we recover the kind of behavior that we would expect, which is that we have a Hall conductivity that is going to go to quantized values, and then as soon as we get to the edge of the gap, we lose that. And as we continue to increase the broadening, you can see how even for very small amounts of broadening, I start to lose the different, if I look at the different components of the cubostrata formula, I start to lose this quantization. However, if you look here, it looks like this would be the part that you would measure. Obviously, when you make a measurement, you're not making a measurement of different components of the cubostrata formula. You're making a complete measurement where everything contributes. And you can see that you get something that looks very nearly quantized. And so as you continue to increase the broadening, that gets worse and worse and worse. So if I were to think about this, then each component of this broadening loses quantization for non-zero broadening, but when you add them together, it looks like it is very, very close to quantization. So we'd like to understand this a little bit more. To do this, we do a little bit more mathematics where we take some asymptotic behavior and expand it. And so we can expand these arctangents, and we can rewrite the Hall conductivities, get rid of some terms that will cancel when we add them together. And we can get a term that is third order in the broadening. And so this would correspond to a term that is very small, where the broadening has a very, very small third order effect on the overall measured Hall conductivity. So if we were to consider then the case of magnetic impurities, which is the one where we saw the qual quantization being close to quantized, then we know that for phase coherence length, it's normally on the order of the sample size. It's largely elastic, and it reproduces quantum fluctuations, as we're well aware. At high temperatures, obviously, it's much smaller, and you don't reproduce the same sort of values. It's a smoother signal that you get from the thermal broadening. So what we can do is we can use Green's functions, the same Green's function we did before, and use a trick where we calculate using the magnetic impurity interaction strength as a parameter, and averaging over all the different components of the carriers scattered throughout the system that we've doped, and calculate the self-energy term to first order, to second order, and look at the part that renormalizes the on-site energy, which just is a shift, and we don't care because it's not adding anything necessarily very interesting, but we also care about the thermal broadening part. Now, I do want to mention that this part, the renormalization, is important if you have a disordered vial semimetal, because you can actually start tilting the bands, and you can go from type 1 to type 2 as you tilt the bands by using this impurity strength. So when we then compare, if I look at the Hall conductivity in total, so this is the complete component with all the different things added into it, then I can identify two different regimes. One corresponds to the ferromagnetic contact, which has a large broadening that it introduces into the system. And so you would expect to live in the right half of the curve, where you see that the quantization is going to be very small if I have a ferromagnetic contact, a metallic ferromagnetic contact. if I were to do the same thing with impurity scattering, I get a different form for the ratio between the broadening and the magnetization components. And so I expect to see nearly quantized conductivity. And so this is the region where they do the experiments in the magnetization with the impurities doped into it. And so this, I hope, gives you an indication of how we can reconcile these two stories together. So my claim is that it's probably not identically quantized, but very close to quantization. So I think we're about close to time. Sheila, is that okay? So then let me just sort of skip then to the, I don't want to run terribly over and just sort of move to the concluding statements that I'd like to make. So I think that this is a really interesting area because I hope I've given you some indication. There's a lot of mathematical things you can play around with this, a lot of theoretical things that you can play around with these combined systems. It really is a truly combined system. It's not where you can really think about it separately anymore between like a topological part and a magnetic part. It's really a combined thing. And you can see this even in some of the experiments where like coercive fields and many other things change when you combine these two things together. So there's a lot of work that's been done and there's more being done now. So it's a really vibrant area with a lot of things to do. I think that the addition of non-Hermitian terms has shown that there's a disconnect. So you have to think about slightly different connections between the mathematics of topology and the observables of topology. And I think that this reexamination has been ongoing, but I think it's very far from complete. You know, everything from arguments that have been made about Weil semimetals and their relation to non-Hermitian systems. I think these are a lot of open questions that remain. And I think that these are going to be things that where if you understand the dynamics of them, it's going to lead to some very interesting physical insights, not only into the basics of magnetism, of topology, but what happens when you combine these two systems together. And so thank you very much for having me. I hope this has been a good talk, and I'm happy to take any questions that you may have.
I applaud for the audience, but they can only do that virtually. Thank you very much for the nice talk. So we have a few minutes for questions. Any questions from the audience?
So these I mean I'm not sure how, but of these, have you seen many? Is topology or these sort of things like these are things that everyone is quite familiar with, or is this something that's very far afield from?
It's a little bit far, I would say. I see one question, Mandela. Do you want to unmute yourself and ask a question?
Yeah, sure. Thanks. Thanks for the nice talk. So when you were discussing the conductivity for a non-Hermitian system, so there was this topological part and this non-topological part. Mm-hmm. Now, I was wondering whether there's not necessarily the conductivity, but whether there's a response function for which that non-topological part could be something like a Hall viscosity or a damping, because I imagine it's basically describing some sort of loss, right?
Right. So there is some work that, so this goes into, so there are a couple ways that I'll answer this question. So one of the first way I'll answer it is, yes, there has been some work on viscosity in these types of systems. I don't think it's really necessarily been applied to topological systems per se. I think it's been applied to Hall systems, which have a topological component to it. But this has really been in terms of, you know, as you said, calculating viscosities. And this gets into the components of artificial gauge fields that you would need in order to be able to impart these sort of, because what you really want to do in order to be able to think about viscosity is to truly think about it in terms of, say, like a torsion tensor. So then you look at the stress energy tensor that results from the fact that you've you've applied some sort of a strain to the system in order to change the electron's viscosity. And so this leads to questions about the types of things that you can observe. And there are very interesting things that you can observe in systems that have this type of viscosity. And that would be things like the Nia-Yan anomaly. So this is where you have a thermal dependence of the conductivity, which has a power law dependence rather than the normal sort of Wiedemann-Franz law dependence. And there are a lot of very deep theoretical issues that surround that. In particular, if you have a field theory such as the Nia-Yan anomaly, then there's inherently a UV cutoff that must exist. And the UV cutoff that exists, it can actually limit the way that you formulate this theory. And so it may look like the terms, the UV cutoff, where you place the cutoff will change the answer depending on where you place the cutoff, which means that it's not a gauge invariant or a properly defined theory. And so there's a lot of questions that surround how to define a quantum anomaly like the Nia-Yan anomaly in such a system because of the fact that there's a difference between consistent and covariant anomalies. But there in the experiment, and so there's also some work that's been done on trying to reconcile some of these questions about viscosity and non-Hermitian behavior by going back to formulations of the Boltzmann transport equation. And in these formulations, so people who've been looking at these formulations, in particular like Sabir Sachdev and Andrew Lucas who's now at Colorado, they've been looking at ways of sort of reconciling like hydrodynamics using viscosity and trying to reconcile that using these sort of topological terms. That's been an ongoing thing. And I know that it's quite contentious because before the last couple of years, I was at Stanford for the last number of years, and there was a talk that was there that was supposedly in principle a friendly talk that became very not friendly when some of the mathematics of these things started coming up. So it's very contentious, but very interesting and very lively. Experimentally, there are points where I think there have been a lot of people doing some, not lots, but I know Amir Yacobi and some of his collaborators have been using NV centers on the tip of a microscope to look at viscous properties of the electron fluid, looking at regions where they can get hydrodynamic flow. So there's been some in each category, but no reconciliation truly between the two of them. So it's an interesting direction, but one that hasn't been fully fleshed out yet.
Thank you.
Long answer to your questions.
Thank you very much.
We can take one quick question. Any quick question from the audience? Right, if that's not the case, let's thank our speaker again, and we'll close the formal session.
Thank you. Hopefully I can visit so I can see the university at some point, because it'd be nice to finally close the loop where I can, you know, the high school student in me gets to come back out again and enjoy the campus. So thanks very much for having me. I hope it was a good talk and that you got something out of it. And again, thanks for the opportunity.
Let me stop the recording.